Hi, I'm Sean Moran with ACC GIS, and our topic today is vector overlay analysis. Now, learning in the ACC GIS program extends beyond the classroom. Each semester, our GISC 2401 data acquisition and analysis and GIS students team up with a local organization to complete a service learning project. Students conceive, design, implement, and complete a GIS project in collaboration with our sponsor to benefit their organization and community. Students often use the vector, raster, and 3D analytical skills you are learning in this class to complete their projects. In 2015, ACC GI students teamed up with the Hill Country Alliance to tackle environmental issues facing Central Texas. You can review these completed service learning projects on the ACC Advanced GIS course Investigates Hill Country Issues webpage on the Hill Country Alliance website. This first project, Blanco River Floodplain Analysis, was completed by ACC GIS graduate Courtney Rowe, who now works for Pape Dawson Engineers. In her analysis, she compared two different floodplains. One floodplain that was in place prior to the 2014 Memorial Day floods, which was the historical FEMA 100-year floodplain, and then at the time, the proposed new 100-year floodplain for Hays County. And she compared the difference in extent of these two floodplains and the impact on surrounding parcels within the context of the 2015 Memorial Day floods. And you can even see a zoom in on a portion of the Blanco River where the original floodplain existed, which is in blue, and the new floodplain exists in red, along with parcels that were impacted by the 2015 Memorial Day flood in yellow. Another project the students completed was a hill country overlay analysis. This project was completed by Angela Gilmeister, an ACC GIS graduate who now works for CP&Y Engineering. For this project, Angela overlaid 100 different published boundaries that define where the Texas Hill Country is, and then combined them into a composite layer that mapped where they were more in consensus or less in consensus. And so in the map there, you can see the greens are where the boundaries were more in consensus, and the browns where they were less in consensus. And she even went so far as to use geostatistical analysis to define the one standard deviational ellipse and also the mean center of the Texas Hill Country, which, interesting enough, is located very close to Lukenbach, Texas. The last project we'll look at is mining impact on watersheds. This project was completed by ACC GIS graduate Yasmin Avila. And she looked at mining industry's impact on Texas Hill Country watersheds, and how she did it is she used TCEQ mining data to locate where mines were in Central Texas, and then used aerial imagery to map the extents of each of these mines. She then overlaid the mines on top of watershed boundaries to determine which watersheds were impacted more or less by these mining operations. Yasmin now works for the City of Austin Watershed Protection. And so note that many of our students use their service learning project and other projects they complete while in the ACC GIS program to create a professional portfolio they can use when applying and interviewing for GIS positions. I also want to point out that many of these projects employ vector overlay analysis, our topic for today. Our objective is to create accurate vector GIS data through overlay analysis. By the end of this topic, you should be able to describe different vector overlay spatial relationships, distinguish between vector overlay query and analysis, list and describe different vector overlay geoprocessing tools, compare and contrast proximity versus overlay analysis, and you'll use vector overlay tools to perform an impact assessment in both the lecture demo and the project. This week, we'll focus on vector overlay queries and analysis, where we'll query and analyze relationships between overlapping features. Let's begin with vector overlay queries, where we select features based on their spatial relationship using the Select by Location geoprocessing tool in ArcGIS Pro. In the Select by Location tool, we set the input features that will be selected using the spatial relationship with the selecting features. And of course, we can set the selection type to create a new selection or to build complex queries by building on a previous selection set. Now, there are a number of spatial overlay relationships that we can utilize to perform a vector overlay query. And if you look at the image on your right, you can see in the relationship drop-down box, I've colored the different spatial relationships to coincide with the different types of overlay relationships. So the overlay relationship intersects includes intersect, intersect 3D, and intersect DBMS. And that's just if the input feature, boundary, or inside intersects a selecting feature, boundary, or inside. And intersect 3D takes into account Z coordinates, and intersect DBMS is utilized when you're performing spatial queries on large enterprise databases. Note that there's a couple of other green spatial relationships that are highlighted, including share aligned segment width and cross by the outline of. Share aligned segment width is just if the boundaries share a line segment, and cross by the outline of is if the boundaries cross. Contains is another type of spatial overlay relationship, including contains, completely contains, and contains Clementini. Contains is if the input features contain the selecting features, and it can be the boundary or the inside. Completely contains mean it must contain both the boundary and the inside. And then contains Clementini means that it contains the inside, but not necessarily the boundary. Contains also includes the spatial overlay relationship have their center in which the center of the input features must fall within the boundary of the selecting features. The spatial overlay relationship within is just the opposite, in which the input features will be selected if they lay within the selecting features. And within includes both the boundary and the inside. Completely within means that both the boundary and the inside needs to be completely within the selecting features. And then within Clementini means the inside, but not necessarily the boundary needs to be within the selecting features. The last type of spatial overlay relationship is identical, and it's pretty straightforward. It means that input features will be selected if they're coincident with selecting features. Now let's take a closer look at each of these vector overlay queries, and we'll start with intersects, in which you select intersecting features. And this is the default and maybe most straightforward form of spatial relationship in the Select by Location tool in ArcGIS Pro. And if you look at the examples in the lower left-hand corner, you can see that I'm utilizing a counties and Texas polygonal layers to perform my Select by Location. And in this case, I've selected the input features as counties, the relationship as intersect, and the selecting features as Texas. So counties that intersect Texas are selected. And if you look in the results, you can see that all 254 counties in Texas intersect either the border or the inside of the state of Texas and are selected. If we look at shares aligned segment in the upper right-hand corner, you can see that my select by location now has the input feature set as counties, the relationship set as share aligned segment width, and the selecting features as Texas. So in this case, only the counties on the border of the state of Texas share a line segment or a border with the state of Texas. And so only those counties are selected. In our last example of the intersects spatial relationship, we've got the input features set to counties, the spatial relationship set to cross by the outline of, and the selecting features is Texas. In this case, only one county is selected. That's Jeff Davis County in far west Texas. And I believe it's because there's a single point that crosses the boundary, and it's really small. I tried to zoom all the way in and I couldn't even see it, but I believe that's why it was selected. Now let's look at the spatial relationship where we can select containing features. And there's three types of contains: completely contains, and contains Clementini. Contains means the inside or the boundary. Completely contains means the inside and the boundary. And contains Clementini means inside and not the boundary. And so if you look at the example in the lower left-hand corner, you can see that I'm running a select by location using contains, and contains Clementine. Where the input feature is set to Texas, the spatial relationship is contains or contains Clementine, and the selecting feature is Lipscomb County, which is the county in the far northeast corner of the panhandle. And in this case, Texas gets selected both times because in the first example, Texas contains both the inside or boundary of Lipscomb County. And in the second example, the inside of Texas contains the inside of Lipscomb County, but the boundary of Texas does not contain the boundary of Lipscomb County, but it is still selected because it contains Clementine, it's inside, not boundary. The last contains relationship is completely contains, in which it includes the inside and the boundary. And if you look in the upper right-hand corner of the slide, you can see again I'm using Lipscomb County, and I've set my select by location parameters as the input features are set to Texas. The relationship is completely contains, and the selecting feature is Lipscomb County. In this case, it does not select the state of Texas, and that's because the inside of Texas contains the inside of Lipscomb County, but the boundary of Texas does not contain the entire boundary of Lipscomb County. It only contains the north and east side of the county, not the west and south side of the county. The spatial relationship within select features that are within the selecting features. And that includes 4 types of spatial relationships: within, completely within Clementine, and have their center within. And so first, let's take a look at both within and within Clementine. Now in the upper right-hand corner, I've run that select by location with those 2 spatial relationships between the counties within and within Clementine, the selecting feature, which is Texas. And in this case, because the counties are within the inside or the boundary, or within inside, not the boundary of the state of Texas, all 254 counties are selected. If you look at the lower left-hand side, you can see I'm utilizing completely within. So in this case, the input features is set to counties, the relationship to completely within, and the selecting features to Texas. In this example, the counties that are not on the border of Texas are entirely within both the boundary and the inside the state of Texas, so they are selected. But the counties that are on the border, the inside is within the state of Texas, but the boundary of each county is right on the line with the boundary of Texas, and it's not within. So they are not selected. The last example on this slide is have their center in, or I like to think about it as have their center within. And so in the lower right-hand corner, I have the select by location tool open and the input feature set to counties, the relationship have their center in, and the selecting features to Texas. In this case, it selects 253 counties. The 254th county that's not selected is Aransas County. And if you zoom in on Aransas County in the central Texas Gulf Coast, you'll see that Aransas County is made up of an island, a peninsula, and the mainland. But the centroid of the county is out over the water. And because the centroid is over the water and not within the boundary of the state of Texas, Aransas County does not get selected. Now, the last spatial relationship we'll discuss is identical, in which input features are selected that are identical to the selecting features. And so in this case, I've got Travis County highlighted and separated as a layer. And if you look in the select by location geoprocessing tool, my input features is set to all 254 counties. My relationship are identical to, and my selecting features is set to Travis County. And so when I click apply, then it only selects the corresponding and identical polygonal feature in the county's layer, which is also Travis County. Now, I've gone through and explained each of these types of spatial relationships that we utilize in vector overlay and vector proximity queries. It's not always obvious to me. And so sometimes I just have to set it to the way I think it's going to turn out and then look at what the results are and compare them to what I thought the results should be. And after I iterate through a few different versions of my query, I typically can settle on the right input features, relationship, and selecting features.